Hello everyone, and welcome to today's presentation. I'm excited to have you here. Today, we'll be exploring the fascinating topic of delivery and routing of IP packets. This is the first slide, which is our cover slide. Over the course of this presentation, we'll cover how IP packets are delivered across networks and the routing mechanisms involved. So let's dive in and get started. Let's dive into what an IP packet actually is. At its core, an IP packet is the fundamental unit of data transmission in an IP network. Imagine it as a small, packaged piece of information that travels across the internet or any IP-based network. An IP packet consists of two main parts, the header and the payload. The header is like the address label on a letter. It contains crucial control information, such as the source and destination IP addresses. This information helps routers figure out where the packet is coming from and where it needs to go, ensuring it reaches the right destination. Now, the payload is where the actual data lives. This could be anything from an email message, a web page, or a file being transferred. Once the packet arrives at its destination, the data inside the payload is passed on to the appropriate application or protocol for further processing. Understanding this structure is key, because it highlights how data is organized and routed efficiently across networks. Every packet, with its header and payload, plays a vital role in ensuring reliable and accurate communication in the digital world. Now let's take a closer look at how routers handle IP packets. When a packet arrives at a router, the first thing it does is examine the IP header. This header contains crucial information, especially the destination IP address. The router uses this address to determine the best route for the packet to reach its destination efficiently. It's important to remember that a packet might pass through multiple routers along the way. Each router reads the IP header, makes a decision based on the routing table, and forwards the packet closer to its destination. Once the packet finally reaches its destination device, the process continues in reverse. The packet is decapsulated, meaning the outer layers are removed, revealing the payload. This is the actual data intended for the application. This process is fundamental to understanding how data travels across networks, ensuring that information gets from one device to another accurately and efficiently. It ties directly into the overall theme of how network communication works seamlessly behind the scenes. When we talk about IP packet delivery, what exactly do we mean? Well, it's a core part of how computer networks work. It involves sending data packets from a source to a destination reliably and efficiently. Delivery, in this context, refers to the entire process of moving that packet across the network, from the moment it leaves the sender until it arrives at its target. Now, routing is a key part of this process. It specifically relates to how routers decide the best path for that packet to take. Think of it like giving directions. Routers evaluate different routes and choose the most optimal one based on current network conditions. Both delivery and routing are fundamental because they ensure data gets where it needs to go, quickly and accurately. As we go through this presentation, keep in mind that understanding these processes helps us grasp the bigger picture of network communication and how data flows seamlessly across the internet. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at this diagram, which illustrates the structure of an IP4 packet header. This header is a crucial part of how data is transmitted across the internet. Essentially, it acts like the address label on a package, guiding information from the source to the destination. Within this header, you'll find several key fields, each serving a specific purpose. For example, the source and destination IP addresses tell us where the data is coming from and where it needs to go. Other fields like the header length, total length, and time to live help manage the data flow and ensure efficient delivery. Understanding this structure is fundamental because it helps us grasp how the internet manages to send packets reliably and accurately. It's the backbone of data transmission, ensuring that information reaches the right place in a timely manner. So, as we move forward, keep in mind that this header is part of the broader IP protocol, which underpins almost everything we do online. It's a vital component that makes the internet work seamlessly behind the scenes. Now, let's take a closer look at the header, which is 24 bytes long. This part of the packet contains some of the most crucial information for routing and delivering the data. Think of it as the address label on a package. Without it, the packet wouldn't know where to go or how to get there. These 24 bytes hold key details that guide the packet through the network, ensuring it reaches the correct destination efficiently. Understanding this header is fundamental because it underpins the entire process of data transfer and communication across networks. It's the backbone that keeps everything organized and on track as the packet moves from sender to receiver. Now let's take a closer look at some of the key fields in the IP header. First up is the version. This simply indicates which version of the IP protocol we're using, like IP4 or IP6. It's essential because it tells devices how to interpret the rest of the header. Next, we have length. This specifies the length of the IP header itself, measured in 32-bit words. Knowing this helps routers and devices understand where the header ends and where the actual data begins. Then there's packet length, which is the total size of the entire IP packet, including both the header and the data, measured in bytes. This is crucial for ensuring that packets are transmitted correctly and reassembled properly. Moving on, we have identification. This field is used to uniquely identify fragments of a larger IP packet. When a packet is too large for a network segment, it gets broken into smaller fragments, and this ID helps reassemble them at the destination. Finally, let's talk about the DF, or Don't Fragment flag. This flag indicates whether the packet is allowed to be fragmented. If it's set, routers won't fragment the packet, which can be important for certain applications that require the packet to arrive intact. Connecting all these points, these fields are fundamental in the IP header because they control how packets are identified, sized, and managed during transmission, ensuring data gets from source to destination efficiently and accurately. Now let's take a closer look at some of the key fields in the IP header. First, we have the MF, or More Fragments flag. This tells us whether there are additional fragments of the original packet coming. It's crucial for reassembling packets that are broken into smaller pieces during transmission. Next, we see the Service Type field. This specifies the kind of quality of service we want for the packet. For example, it can prioritize voice calls over regular data, ensuring better performance for time-sensitive applications. Then there's the Time to Live, or TTL. Think of this as a safeguard. It's a counter that decreases each time the packet passes through a router. When it hits 0, the packet is discarded. This prevents packets from endlessly circulating in the network, which could cause congestion. Moving on, we have the Transport field. This indicates the next-level protocol, like TCP or UDP, used in the data part of the packet. It helps the receiving system understand how to process the payload properly. Finally, the header checksum is used for error checking. It helps verify that the header data wasn't corrupted during transmission. If the checksum doesn't match, the packet can be discarded or flagged for retransmission. All these fields work together to ensure our data is delivered accurately, efficiently, and with the right priority, highlighting the robustness of the IP protocol in managing network communication. Now let's take a closer look at the key components of an IP header. First, we have the source IP address, which is simply the IP address of the sender. This tells the recipient where the data is coming from. Next, there's the destination IP address, indicating the intended recipient of the data. Both of these addresses are essential for directing the packet through the network. Moving on, we see the Options field. This is optional but can be used to add extra functionalities or information, like security or routing options. It's not always used, but it provides flexibility for specific needs. Then there's padding. Padding is used to make sure the header length is a multiple of 32 bits. Think of it as filling in space so everything lines up properly, which helps with efficient processing. Finally, we reach the data section. This is the actual payload or content that's being transmitted. It could include data from higher layer protocols like TCP or UDP. Essentially, this is what the entire transmission is about, the information that needs to reach the destination. Understanding these components helps us see how IP packets are structured to ensure reliable and efficient data transfer across networks, which ties back to the overall theme of network communication and protocol functionality. Now let's talk about the types of IP packet services. There are two main categories: connection-oriented service and connectionless service. Connection-oriented service is like making a phone call. There's a setup phase, a dedicated path for the duration of the communication, and then a teardown when you're done. It ensures reliable delivery, ordered packets, and error checking. On the other hand, connectionless service is more like sending a letter. You just send the packet without establishing a dedicated connection beforehand. It's faster and more flexible, but doesn't guarantee delivery or order. Understanding these two types helps us see how different network applications prioritize reliability versus speed. This distinction is fundamental to grasping how IP handles various types of data transmission across networks. Let's talk about connection-oriented services. Essentially, this type of service involves setting up a dedicated path between the source and the destination before any data is actually transferred. Think of it as establishing a private, reliable highway for your data to travel on. This setup ensures that the data arrives in the correct order and without errors, which is crucial for many applications. A key part of this process is the handshake method. This is how the sender and receiver agree to communicate and establish that dedicated connection. It's like a handshake in person, confirming that both parties are ready and synchronized before starting the actual transfer. Once the connection is established, it remains open until all the data has been successfully transmitted. This guarantees dependable delivery, meaning your data isn't lost or corrupted along the way. A common example of a connection-oriented service is TCP, or Transmission Control Protocol. TCP ensures that data packets are delivered accurately and without errors, making it reliable for most internet activities like web browsing, email, and file transfers. So, in summary, connection-oriented services create a reliable, ordered, and error-checked communication channel, which is vital for many applications that require precise and trustworthy data transfer. Let's look at some examples of connection-oriented services. First, we have TCP, or Transmission Control Protocol, which is part of the TCP IP suite that underpins the Internet. TCP is a classic example because it establishes a reliable connection between sender and receiver before data transfer begins, ensuring that all data arrives intact and in order. Next, think about traditional telephone calls. They also rely on a connection-oriented approach. When you make a call, a dedicated connection is established between the two parties, and this connection stays active for the duration of the conversation. Both of these examples highlight the core idea of connection-oriented services, creating a reliable, continuous link between communicating entities. This approach is crucial when data integrity and order are priorities, and it ties into our overall discussion on how different network services operate to meet various communication needs. Let's take a closer look at some key features of connection-oriented services. First, they establish a dedicated connection, which can be either logical or physical, before any data transfer begins. This means that both ends agree on a path or a channel to communicate, ensuring a reliable link. Next, reliable transmission is a cornerstone. Data is sent with error checking, acknowledgements, and if necessary, retransmissions. This process helps guarantee that the data arrives intact and correctly at the destination, which is essential for applications that require accuracy. Sequencing is also vital. It ensures that data packets arrive in the correct order, even if they take different routes or experience delays along the way. This maintains data integrity and makes sure everything is assembled properly at the receiving end. However, it's important to recognize that these features come with a trade-off: higher overhead. Establishing and maintaining this connection requires extra resources and processing power, which can impact performance. Overall, these key features highlight how connection-oriented services prioritize reliability and order, making them ideal for situations where data integrity is crucial, even if they involve some additional overhead. So let's talk about reliable data transfer. This is all about making sure that every piece of data actually reaches its destination without any errors along the way. It's like ensuring that a message you send doesn't get scrambled or lost. Next, we have data sequencing. This is really important because it guarantees that packets of data are delivered in the correct order. Imagine receiving a letter where the pages are all jumbled. It's confusing. Sequencing makes sure that everything is in the right place, making the data meaningful once it arrives. Then there's error correction. During transmission, errors can happen, but with these mechanisms in place, errors are detected and corrected automatically. This way, the integrity of the data is preserved, and what you receive is exactly what was sent. Finally, guaranteed delivery. If some data gets lost or doesn't arrive, retransmission kicks in. The system will resend that data until it's confirmed to be received correctly. All of these features, reliable transfer, sequencing, error correction, and guaranteed delivery, really highlight the advantages of connection-oriented services. They provide a dependable, orderly, and error-free communication channel, which is essential for many applications where accuracy and completeness are critical. This ties directly into our overall theme of ensuring robust and trustworthy data communication. Let's take a closer look at some of the disadvantages of connection-oriented services. First, higher latency is a key issue. When establishing a connection, there's an initial delay before any actual data can start transferring. This setup time can impact overall performance, especially in time-sensitive applications. Next, there's more overhead involved. Maintaining a connection requires additional resources, such as handling acknowledgments and retransmissions when packets are lost. This extra effort can strain network resources and affect efficiency. Finally, connection-oriented services tend to be less efficient for small transfers. If you're sending just a short message, the time and resources spent on setting up and tearing down the connection might outweigh the benefits of reliable delivery. So, while connection-oriented services offer reliability, these disadvantages highlight why they might not always be the best choice, particularly for quick, lightweight exchanges. Let's talk about connectionless services. These services send data without setting up a dedicated connection between the sender and the receiver. Think of it like sending individual postcards rather than opening a phone line. Each packet of data is treated independently. Because of this, there's no guarantee that the data will arrive or even arrive in the right order. Basically, connectionless services do not promise reliability. Another key point is that packets don't follow the same path to reach their destination, which can make delivery faster but also less predictable. Each packet is sent separately, so we can't ensure they arrive in order or correct any mistakes along the way. This makes the process quicker, but it also means it's less dependable. A common example of this is UDP, the User Datagram Protocol. It's often used in streaming applications, like live video or audio, where speed is more critical than perfect accuracy. So, in essence, connectionless services prioritize speed and efficiency over guaranteed delivery, fitting well with applications where some data loss is acceptable. Let's look at some examples of connectionless services. One common example is UDP, or User Datagram Protocol, which is part of the TCP/IP suite. UDP allows data to be sent without establishing a formal connection first, making it faster but less reliable. Think of it as sending a message without waiting for an acknowledgement. Another example that many of us can relate to is postal services. When you send a letter, you don't get a confirmation that it was received. You just trust that it will arrive. This is similar to connectionless communication, where there's no ongoing connection or confirmation process between sender and receiver. These examples highlight the core idea of connectionless services. They prioritize speed and simplicity over guaranteed delivery. This ties into the overall theme of understanding different communication methods and their trade-offs in network design. In this slide, we're focusing on the key features of connectionless services. First, there's no connection setup, which means data is sent directly from sender to receiver without going through any prior handshake or establishing a dedicated connection. This allows for quicker data transfer since we skip the setup phase. Next, we have independent packets. Each packet is treated as its own individual unit, and because of that, they might take different routes through the network to reach the destination. This makes the transmission more flexible and resilient to network changes. Speaking of speed, one of the biggest advantages here is faster transmission. Because there's no time spent establishing or tearing down a connection, data can flow more quickly. However, this comes with a trade-off. It's unreliable. There's no acknowledgement that the data was received, no retransmission if it gets lost, and no error correction. So, while connectionless services are efficient and fast, they're best suited for applications where some data loss is acceptable. Overall, these features highlight a very different approach to data transfer, focusing on speed and simplicity rather than guaranteed delivery. Let's take a moment to look at some key advantages of connectionless services. First, they offer low latency, meaning data is transmitted immediately without the need to wait for a connection to be established. This makes them really quick for sending small pieces of information. Second, they're especially efficient for small transfers, such as DNS lookups or VoIP calls, where speed is crucial and the messages are usually brief. Third, these services are highly scalable. Since there's no need to maintain a dedicated connection for each user, they work well even when many users are accessing the system simultaneously. Overall, these features make connectionless services ideal for scenarios where speed, efficiency for small data, and scalability are important. Now, let's take a closer look at some of the disadvantages of connectionless services. One key issue is that data packets can be unreliable. This means packets may get lost along the way, duplicated, or even arrive out of order. Such unpredictability can pose significant challenges for applications that need consistent and ordered data delivery. Another important point is that connectionless services lack built-in error handling. There are no automatic mechanisms for retransmitting lost packets or correcting errors, so the responsibility often falls on higher-layer protocols if reliability is needed. Additionally, this type of service isn't suitable for large transfers. If you're dealing with big files or data streams that require reliable and sequential delivery, connectionless services may not be the best choice. Overall, while connectionless services offer simplicity and speed, these disadvantages highlight why they might not be ideal for applications demanding high reliability and order. Let's talk about IP packet delivery and routing, which are really the backbone of how data moves across computer networks. When we say delivery, we're referring to the entire process of getting a data packet from its source to its destination. It's like sending a letter through the postal system. It involves multiple steps and different network components working together. Routing, on the other hand, is more specific. It's about how routers decide the best path for that packet to take through the network. Think of routers as the traffic managers. They analyze various factors like network congestion, link costs, and policies to determine the most efficient route. Understanding these processes is crucial because they ensure that your data arrives quickly and reliably. Whether you're browsing the web, streaming a video, or sending an email, IP delivery and routing work seamlessly behind the scenes to make it happen. So, in essence, delivery is the overall journey, and routing is how that journey is planned and managed. So, what is IP routing work all about? Well, at its core, IP routing is the process that determines how data packets travel across networks to reach their destination. It's like the GPS of the internet, guiding packets from one point to another efficiently. When we talk about IP routing, we're focusing on the key role it plays in connecting different networks and ensuring data gets where it needs to go. This involves making decisions based on IP addresses and routing tables, which contain information about the best paths available. Understanding this helps us see how networks communicate seamlessly, even across vast distances. Essentially, IP routing work underpins all internet activity, enabling us to browse websites, send emails, and stream videos. It's the backbone that keeps our digital world moving smoothly. Now, let's talk about how IP routing actually works. Essentially, IP routing is the process of directing information from its source all the way to its final destination. Think of it as a journey that data takes across a network. As we know, data isn't sent as a single chunk. Instead, it gets broken into smaller pieces called packets. These packets don't all follow the same path. They often pass through multiple routers along the way. Each router plays a crucial role by examining the packet's destination address and deciding the best next step for that packet. This decision-making process is guided by a routing algorithm, which determines the most efficient path based on various factors like network topology and current traffic conditions. The overall goal here is to ensure that each data packet reaches its destination accurately and efficiently. So, in essence, IP routing is all about choosing the right path for your data, navigating through the network, and making sure it arrives safely. This process is fundamental to how the internet and modern networks keep everything connected seamlessly. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at this IP routing diagram. It illustrates the process of IP routing, which is essentially how data packets travel from one machine to another across a network. Starting with the source machine, this is where all the data begins its journey. Think of it as the origin point for our information. From here, the data moves into Network 1, which represents the first segment of the network connected to the source. This diagram helps us understand the key concept that IP routing involves directing packets through various network segments to reach their destination. Each step, whether it's through different networks or routers, ensures that the data gets closer to its target. Understanding this process is fundamental because it underpins how all our network communication works, whether we're browsing the internet, sending emails, or streaming videos. It's the backbone of network connectivity, making sure data finds its way efficiently and accurately from source to destination. Now, let's take a closer look at the routers depicted here, labeled R1, R2, R3, and R4. These cylindrical shapes are representing routers, which are essential network devices responsible for forwarding data packets between different networks. Their main job is to determine the best possible path for each packet to reach its destination efficiently. Think of them as traffic controllers that direct data along the optimal route. Moving on, we see Network 2, which signifies the network segment where the destination machine is located. This is the final destination for the data packets we're examining, and it's crucial that the routing process gets the packets here accurately. Finally, at the end of this path, we have the destination machine. This is where the data packets are ultimately received and processed. It's the endpoint of our data journey. Connecting all these points, the routers work together to navigate the complex network landscape, ensuring that data packets reach their destinations swiftly and reliably. This process highlights the importance of routing in maintaining effective communication across networks, which is a core theme of our presentation. Understanding how data finds its way across interconnected systems. Let's walk through how IP routing works in this diagram. First, imagine data packets starting from the source machine and entering Network 1. From there, these packets are sent to R1, which acts as the first router in the path. R1 then forwards the packets to R2, which continues the journey by routing them further along the network. Next, R2 sends the packets to R4, which again examines the destination and makes the routing decision. From R4, the packets are directed to R3, the final router before reaching the destination network. R3 then routes the packets to Network 2, from where they finally arrive at the destination machine. This sequence highlights how each router plays a crucial role in guiding data through different networks, ensuring it reaches the correct destination efficiently. It's a great example of how IP routing enables seamless communication across complex networks. This entire process ensures that data finds its way efficiently from one point to another across potentially complex network infrastructures. What's really important here is how multiple routers come into play to navigate these different network segments. Each router acts like a traffic director, helping data packets move smoothly through various parts of the network. By utilizing these multiple routers, the network can handle complex routing paths, avoid congestion, and ensure that information reaches its destination quickly and reliably. This concept ties back to the overall theme of how robust and adaptable our network systems need to be to support seamless communication in today's interconnected world. Today, let's talk about the different types of deliveries. There are two main kinds: direct delivery and indirect delivery. When we say direct delivery, we're referring to a situation where the product or service goes straight from the provider to the customer, without any middlemen involved. It's straightforward and efficient. On the other hand, indirect delivery involves intermediaries, like wholesalers or retailers, who help get the product to the final customer. Now, you might be asking, what do we really mean by delivery in this context? Well, delivery is essentially the process of transferring a product or service from the provider to the customer. It's a critical part of the overall supply chain because it ensures that what we offer reaches the end user in the right condition, at the right time, and in the right place. Understanding these two types of delivery helps us see how companies can choose the most effective way to serve their customers, whether they opt for a direct approach for speed and control, or an indirect approach for wider reach and scale. This ties back to our overall theme of optimizing logistics and customer satisfaction. All right, let's talk about direct delivery. This happens when the destination host is on the same physical network or subnet as the sender. In other words, they are on the same local network segment. When this occurs, the packet doesn't need to be sent to an intermediate router for forwarding. Instead, the sender can directly figure out the destination's MAC address, usually through ARP for IP4. Once it has that MAC address, it encapsulates the IP packet within a data link frame and sends it straight to the destination. This process makes communication more efficient because it avoids unnecessary routing steps. So, in essence, direct delivery is all about local, quick, and straightforward packet transfer within the same network. Let's walk through how direct delivery works. First, the network identification step. The sender, which could be a host or a router, examines the destination IP address. This is a crucial step because it helps determine where the packet needs to go. Next, we apply the subnet mask to the destination IP address. This allows the sender to figure out the network address of the destination. Think of the subnet mask as a filter that separates the network part of the IP from the host part. Once we have the network address, the sender compares it to the network addresses of its own local networks. If the addresses match, the packet is destined for a device within the same network, and it can be delivered directly. This process highlights the efficiency of direct delivery, sending data straight to its destination within the local network without unnecessary routing. It's a fundamental concept that keeps data moving smoothly and quickly across networks. Now let's look at the concept of direct transfer. Essentially, if the destination's network address matches one of the sender's connected networks, the packet doesn't need to go through any extra steps. Instead, it is sent directly to the destination host on the same physical network segment. This is what we call direct delivery. It's a straightforward process that happens when both source and destination are on the same local network. This method is efficient because it avoids unnecessary routing or forwarding, making communication faster. Understanding this helps us see how devices communicate smoothly within the same network segment, which is a fundamental part of network operations. When we talk about direct delivery, we're looking at situations where data packets go straight to their destination without needing to be relayed through other devices. First, imagine two hosts on the same network, like two computers connected to the same Wi-Fi or Ethernet. In this case, when one host wants to send a packet to the other, it simply sends it directly onto the local network. The packet is delivered straight to the other host without any intervening steps. Next, consider a scenario with a router. If a router needs to deliver a packet to a host on its own network, it does so directly. That means the router recognizes that the destination device is on the same physical network, and it sends the packet straight to that device. This process is efficient because it avoids unnecessary routing or forwarding steps. These examples highlight the importance of understanding when direct delivery occurs, as it impacts network efficiency and speed. It's a fundamental concept because, in many cases, local communication is the fastest way for devices to share information. Recognizing these situations helps us better design and troubleshoot network systems. Now let's talk about indirect delivery of an IP packet. When the destination host is on a different network than the sender, the packet can't go straight there. Instead, it needs to be forwarded through one or more intermediate routers. Essentially, the packet makes its way across multiple networks until it reaches its final destination. The sender starts by checking its routing table to find the default gateway or the next router to send the packet to. Once identified, it sends the packet to that router's physical, or MAC, address. This process continues, with each router forwarding the packet closer to the destination, until it finally arrives at the router connected to the destination network. This whole process highlights the importance of routing tables and MAC addresses in guiding packets across different networks, ensuring they reach the right destination even when they're not on the same local network. It's a fundamental part of how data travels efficiently across the internet and other interconnected networks. Now, let's look at the first step in indirect delivery. The sending host needs to figure out whether the destination IP address is on its own local network or on a different one. To do this, it uses the subnet mask. By applying the subnet mask to the destination IP, it determines if the address belongs to its own network or not. If it's not on the local network, the host recognizes that it needs to send the data indirectly. Moving on to the second step. Once the host has established that the destination is outside its network, it consults its routing table. This table is like a directory that tells the host where to send packets for different networks. The host looks up the entry for the destination network. If it finds a specific route, it will use that. If not, it defaults to the default gateway, which is essentially the next router to forward the packet towards the destination. These steps are critical in understanding how data finds its way across different networks, ensuring it reaches the right destination efficiently. This process exemplifies the broader theme of how networks communicate across boundaries using routers and routing tables. Now let's look at what happens in step 3, which is encapsulation for the next hop. At this point, the IP datagram is wrapped inside a frame, such as an Ethernet frame. The key here is that the frame's destination address is the MAC address of the next hop router. This step is crucial because it prepares the packet for physical transmission over the network link. Moving on to step 4, packet forwarding. The frame is then sent out to the next hop router. Think of this as the packet being handed off to the next delivery vehicle in its journey. Then in step 5, the router receives the frame. It decapsulates, meaning it removes the Ethernet frame to get back to the IP datagram. The router then checks its own routing table to decide where to send the packet next. It could be another router if the destination is still far away, or it might be the final destination network. These steps are fundamental to how data travels across networks. They show the seamless process of encapsulation, transmission, and routing decisions that keep our communications moving efficiently from source to destination. So, in step 6, the process of packet forwarding is repeated. This means the packet travels from one router to the next, step by step, getting closer to its destination. It's like passing a message along a chain of friends until it reaches someone who's directly connected to the destination's local network. The key point here is that each router examines the packet's address and then forwards it accordingly, ensuring it moves along the most efficient path. Then we arrive at step 7, which is the final stage, direct delivery to the destination. At this point, the last router recognizes that the packet's destination is on its local network. So, instead of forwarding it further, it sends the packet directly to the destination host. This final step is crucial because it's where the packet reaches its intended recipient, completing the journey. Connecting this to the overall theme, it highlights how the network's routing process ensures data efficiently reaches the right device, even across multiple networks. It's a coordinated process, with each step playing a vital role in successful communication. Let's take a closer look at some key elements that keep our networks running smoothly. First up are routers. These are Layer 3 devices, which means they operate at the network layer. Their main role is to connect different networks, and they're essential for making sure data can travel indirectly between devices that aren't on the same local network. Without routers, our internet wouldn't be able to send information across diverse networks seamlessly. Now, moving on to the routing table. Think of this as a kind of map stored within hosts and routers. It contains all the necessary information about different network paths. When a packet arrives, the routing table helps determine the best way to send that packet toward its destination. It guides the data through the network, ensuring it takes the most efficient route possible. Connecting these ideas, routers use their routing tables to make smart decisions about where to send data. This process is fundamental to how data moves across complex networks, supporting reliable and efficient communication. So, understanding these key elements really helps us grasp how networks operate behind the scenes to keep everything connected smoothly. Now, let's talk about the default gateway. The router acts as a kind of traffic manager for our network. Its main job here is to send packets to networks that aren't directly connected to the source host. Think of it as the router's way of guiding data toward destinations beyond its immediate reach. Next, we have ARP, which stands for Address Resolution Protocol. This is a crucial process that devices use to find out the physical, or MAC, address of the next hop router on the local network. Essentially, when a device needs to send data to another device outside its local network, it uses ARP to identify the MAC address of the router that will forward that data onward. Connecting these points to the bigger picture, both the default gateway and ARP are about ensuring data gets where it needs to go efficiently and accurately, especially when crossing network boundaries. They are fundamental components that help maintain seamless communication across different parts of a network. Now, let's take a closer look at how data gets from one point to another. This involves understanding the difference between direct and indirect delivery. Direct delivery occurs when both the sender and receiver are on the same network. In this case, the packet can be sent directly to the destination's physical address, making the process quick and straightforward. On the other hand, indirect delivery comes into play when the destination is on a different network. Here, the packet can't go straight to the recipient. Instead, it needs to be forwarded through intermediary routers, which guide the packet along the correct path to reach its destination. This distinction is important because it highlights how the network handles different scenarios efficiently, ensuring data gets where it needs to go, whether directly or via multiple steps. It ties back to our overall theme of how networks manage communication seamlessly across various environments. When we look beyond just the size of the packet and the header length, the design of the routing algorithm considers several other important factors. These factors help ensure that data takes the most efficient and reliable path from the sender to the destination. At the moment a datagram arrives at a router, the router uses the source and destination address fields embedded in the packet. These addresses are crucial because they tell the router where the data is coming from and where it needs to go. The router then consults its routing table. Think of it as a map of the network to determine the best next step for the data. Essentially, based on the destination address, the router decides which neighboring router or node should handle the packet next. This process is fundamental because it ensures that data finds the most suitable route, considering not just the shortest path, but also factors like network congestion, link reliability, and policy rules. In the bigger picture of network communication, this decision-making process is what keeps data flowing smoothly and efficiently across complex networks. It's a dynamic, intelligent process that adapts to changing network conditions, helping us maintain robust and reliable data transfer. Let's talk about IP packet delivery and routing, which are core processes in how computer networks function. When we say delivery, we're referring to the overall process of moving a data packet from its source all the way to its destination. It's like the entire journey of the packet across the network. Routing, on the other hand, is more about the decision-making process, how routers figure out the best path for that packet to take. Think of routing as the GPS for data packets, guiding them through the network efficiently. Both delivery and routing are fundamental because they ensure that data reaches its destination accurately and quickly. This ties into the overall theme of network communication, making sure data travels reliably and optimally through complex systems. Now, let's move on to slide 44. This slide introduces a quick quiz consisting of 10 multiple-choice questions based on the content we've covered so far. The purpose here is to reinforce your understanding and help you gauge how well you've grasped the key concepts. As we go through these questions, think about the main points we've discussed and how they connect to the overall theme of the presentation. Remember, the goal is not just to get the right answers, but to deepen your understanding of the material. So, stay engaged, and let's see how well you've absorbed the information so far. So, let's talk about the primary function of the destination IP address in an IP packet header. Now, out of the options, the key role is to help routers determine where to send the packet. Think of the IP address as the destination's mailing address. It guides the packet through the network to reach the correct device. It's not about specifying the payload length or containing the actual data. That's handled elsewhere in the packet. And while the IP protocol version, like IP4, is indicated in the header, that's not the purpose of the destination address itself. Understanding this is crucial because it highlights how IP addresses function as the routing guideposts in our network communications, ensuring data gets to the right device efficiently. All right, let's take a closer look at this question. It's asking about a specific IP header field that prevents packets from circulating endlessly in a network. Now, why is this important? Well, in a large network, packets can sometimes get caught in loops, which can waste bandwidth and cause congestion. To prevent this, IP packets include a field that helps control their lifespan. And that field is the time to live, or TTL. Basically, every time a packet passes through a router, the TTL value gets decremented by 1. If the TTL reaches 0, the packet is discarded. This ensures that packets don't keep looping forever. It's like a built-in expiration date. The other options, like identification, header checksum, or service type, serve different purposes, but none of them prevent endless circulation. So the key takeaway here is that the TTL field is crucial for maintaining network health and efficiency by controlling how long a packet can live in the network. This concept ties back into the overall theme of understanding how IP protocols manage data flow and prevent issues like infinite loops. So let's talk about the direct delivery of an IP packet. Essentially, this happens when the packet travels directly from the source to the destination without passing through multiple routers. When the source host recognizes that the destination is on the same local network, it can send the packet straight there. This is a key point because it simplifies the delivery process and reduces network traffic. Another important aspect is the use of the default gateway. When the source host needs to send a packet to a device outside its local network, it uses the default gateway to route that packet. But in the case of direct delivery, if the source and destination are on the same network, the default gateway isn't involved at all. Now, this concept hinges on whether the hosts are on the same physical network or subnet. If they are, the packet can be sent directly. If they're on different networks or subnets, the packet must go through routers to reach its destination. So, in summary, direct delivery occurs when the source and destination hosts are on the same physical network or subnet, allowing for a more straightforward, efficient transfer without passing through multiple routers. This is a fundamental concept that helps us understand how IP packets are routed and delivered efficiently depending on network topology. Great question. The first step a sender takes to determine if direct delivery is possible is to consult the routing table for the default gateway. This routing table helps the sender understand where to send the packet if the destination is outside its local network. It's like checking a map to see if the destination is within reach or if it needs to go through a gateway. The other options, like encapsulating the packet in a frame or applying the subnet mask, happen later in the process. Decrementing the TTL is also important, but that occurs after you've determined where to send the packet. So, Thinking about the initial decision, consulting the routing table is the key first step in the process of packet delivery. Now let's take a closer look at this routing process. We start from the source, then the packet moves through net 1, R1, R2, R4, R3, and finally reaches net 2 before arriving at the destination. The key question here is, which router actually forwards the packets directly to the destination machine's network? Among these options, R1, R2, R3, or R4, the answer is R3. R3 is the router that has the direct connection to the destination network, so it knows exactly how to send the packet straight to the destination machine. Understanding which router handles this final step is crucial because it highlights how routing decisions are made at each point in the network, ensuring efficient delivery. This example underscores the importance of routers knowing their specific network boundaries and forwarding packets accordingly, which ties back to the overall theme of how routing tables and network topology work together to facilitate smooth data transfer.